We can hear you.
Dokey. All right, so let's pick up where we left off last time. So we've been looking at some of the introduction to scheme stuff as we start talking about the constructs of a programming language. We had rolled back to here, our usual slide, how human beings solve problems, memory, asking questions, and repetition. So that's going to be effectively our target for creating a programming language. How do we represent a variable environment, memory, that kind of stuff? How do we allow ourselves to ask questions? We'll have to implement if statements, implement switch statements, whatever. How do we write loops and stuff, especially in Scheme where officially loops don't exist. There are some constructs now that exist, but I think I mentioned last time you're officially not allowed to use them. So you'll be solving everything in here recursively. So we're going to have to hit these targets for writing our own programming language. So we started looking at some scheme functions. I mentioned last time that one of the reasons that I use scheme in here is that it's a very small language. So it doesn't give you too much like extra stuff for heavy lifting. So you have to do all the heavy lifting yourself. And we looked at some of those last time. We looked at cars and cooters. We talked about predicates, which are effectively like Boolean test functions. They are a function that takes a single parameter, returns typically true or false. We looked at kind of one that allows us to test whether a list is the empty list. So that's the null predicate. And that's going to be something that's going to be very common for us to use, this null predicate, because a lot of times that's going to be the end of our recursion. You know, we keep calling something recursively over and over and over again until we finally run out of crap inside the list to deal with. And how do we find that out? We ask to see, is the list empty? If it's empty, no more recursive calls. Okay. Talked about the construct for conditionals, two different ones built into Scheme. So we have an if statement that lets you do an if, single true or false. Now, nothing says you can't nest ifs inside of each other. You can't say, if something is true, do this, else, if something else is true, do something else. I mean, you can certainly put a whole bunch of ifs inside of each other with lots and lots and lots of parentheses. But we have this alternative, a con, that allows us to have multiple different Boolean cases to test. At the end of class last time, we started talking about Lambda expressions. Now, before we jump into that, I'm going to, let's just write something in Java here real quick. Oh, that's not my, actually, don't I have the thing to hide this? Nailed it. So let's say we were writing a function in Java. So we might have something like int add nums, int a, int b, return a plus b, something like that. Okay, so that's what we're looking at here in Java. But if we were to kind of explode this out, so we look at this, we say this is a method, right? It's a method that returns an integer, takes in two parameters, and ultimately does something. In this case, it adds the two parameters together and returns the result, or boils down to the result. All right. Now, if we wrote this in a little bit different way, especially if we consider this in a non-strongly typed setting where we didn't necessarily have to advertise what our return type was, we could do something like this. We could say that we have a variable named add nums that is equal to this, which is a function. Okay, so this is still using memory, still remembering stuff. We have a structure here. We have a value. This is no different than having an integer as a value, or a string as a value, or a char as a value. It just so happens that this value is a function. And we're associating that guy with a variable name, add nums. All right. So and this isn't just Scheme. This is a lot of more modern languages have Lambda expressions built into them. A Lambda expression is the value associated with the function. So in this particular case, this part right here would be the Lambda expression, as opposed to this guy, which is just a variable name that happens to hold a value. So we could say a equals 5, or we could say add nums equals all this crap. Make sense? It's just a name value pair. Nothing more, even though it just seems like functions are a little bit more complex than like an int or a string or something like that, but they're just another kind of value that we need to store somewhere. Why do we need to store it somewhere? Well, because we might, we might need to call it multiple times. That's kind of our rule of thumb for when do we put something in a variable. We put it in a variable when you need to use it more than once, something like that. So that would imply that if we had a function that we were only going to use one time, that maybe seems relatively unlikely, but it's not completely unfounded. It happens, right? If we had a function that we were only going to use one time, why store it in a variable? Why take up memory space on a permanent basis for it when we could just pass the function in? The literal, it's a function literal. Go ahead. Well, then you put it in a variable. If later on you run into a situation where you need to call it more than one time, you're like, okay, I better backtrack and go throw it in a variable so I can call it here and call it here. Yeah, so, I mean, sometimes hopefully you would know most of the time ahead of time, but that's the nice thing with, computers is we don't have to go back and throw out a wad of paper, or in the early days of programming, we had the punch cards, and all of a sudden you're like, okay, well, I got to go rewrite this program. There's a couple backspaces and you're back in business, right? All right, so then back in this slide here, a lambda expression is an unnamed function. We can also think of this as a function literal. That is to say, the value associated with a function. So then we need to sort of ask the questions, well, what is the anatomy of a function? So functions have 0 or more parameters and a logic body that likely does something. Doesn't actually have to do anything, but probably does something. Otherwise, you really start questioning, why did I write any of this, right? Like if you had a function that takes no parameters and does nothing, you kind of just wasted characters, is what you did. All right. Now, if any of you have ever done anything with JavaScript, is kind of a good example where this comes into play. A lot of times when you have like an on button click or something like that, you have something that usually in the documentation in JavaScript is called a callback function, something like that. So if we use an example here. So examples of modern uses of Lambda. I'm saying modern in that things that seemingly pop up in current day programming practice, not something left over from a long time ago, because I want to make sure that it's clear that this Lambda thing isn't some ancient theoretical thing that doesn't come into play anymore. So we might say something like in JavaScript, it is common to pass what's usually called a callback function to, usually it's a multi-threaded thing, to a multi-threaded function call. The callback function will automatically get called when the threaded function finishes. So what's when I say multi-threaded, what does multi-threaded mean? When do we write something that runs inside of a thread? What are we trying to accomplish when we put something in a thread? Good. Yeah, so we're trying to say, hey, I want my program to keep going here, but I want this other stuff to also happen at the same time. So I'm going to go ahead and spawn off a little worker bee, spawn off a thread, and have him go over here and do his thing. All right. Now, but we might say, and so if that is completely autonomous, let's say we're not having any user interaction on our end with that, we're still going on with our program here, it might be in our best interest for it to say, you know what, when this guy is done, go ahead and call this function, which maybe sets a variable back over here, so that later on I can ask the question, did this finish? Or who's currently logged in? Something like that. You know, I kind of want to have like a finishing ninja move at the end of whatever logic was happening. And that's a lot of times what that callback function is used for. Okay. But typically when you pass a callback function, you're not passing in a variable name associated with the function. Instead, you actually can, but usually that's not what you're doing. Usually you're passing in an inline function. It's actually passed in as part of the parameters to the thing. All right. So that's what a callback function typically is. The correct vocabulary for that is, so we might say officially, a callback function is known as a closure. That's just the kind of animal that it is something called a closure. Doesn't matter. You don't have to memorize that or anything. That's just, if you ever come across that word, that's what it's referencing. All right. Syntax for a lambda is the word lambda. It is in lowercase, but Keynote here doesn't like, it wants to self-correct me. So lambda, notice it's all in a list. Scheme's a list-based language, so it's going to be pretty much all the time. You're going to have your stuff contained in a list. I think a question came up last time asking about what those quotes, the little quote before if I had a quote, something like this, A, B, C, something like that. What's this guy here for? As opposed to A, B, C. The difference between these is this is the literal list containing a capital A, a lowercase b, a lowercase c. Whereas this guy here is trying to apply a function whose name is A to the parameters B and C. So it's going to try to look up this variable name inside the variable environment, finding a lambda that it can then apply to two parameters. Probably not what we meant here, right? Because we're going to use lists pretty often. So that's where that little quote thing comes in. It's saying, don't execute this as if it's a function. Treat this as if it's a list of crap. All right, makes sense? All right, so let's go look at some lambdas in the wild. All right, so we looked at some cons and stuff like that. Just to give you an example down here, let's write that same version of add nums. Actually, I'm going to write it up here just so we can because effectively this is our program that's up here. That way I don't have to type it over and over and over again down here. I'll just type it once and run it again. But I'm not going to put it in a variable. I'm going to say, here's my lists. And remember, I just said a few minutes ago that if we don't quote a list, it'll take that very first element, treat it as a function, and apply it to the rest of the elements as parameters. So my first element here is going to be a lambda that takes in an A and a B, 2 parameters, and returns A plus B. And I'll apply that to 5 and 6. So this whole thing is a list. My first element of this list is an unnamed function, is a lambda. So this is a function that takes 2 parameters that I happen to have named A and B. And what does it do with the parameters? Here's the logic body of that function. What does it do with them? It calls so again, here's another list. First element is a function, because I didn't quote it. So we could probably make a pretty good guess at what the function with the plus sign associated with it does. Probably does some adding stuff, right? All right. So this guy adds A and B together, boiling down to the result. So this guy right here is a function that I am now calling with these 2 parameters. 5 will come in as A, 5 will come in as A here, 6 will come in as B, we'll add them together, and we'll get an 11. That makes sense? Now, I did not associate this function with a variable name. I could have. I could take this guy, and then I can say I want to define a variable. Let's call this guy add nums, and we're going to say add nums is equal to that lambda. And then I can say add nums 5 and 6. But I could also say add nums 13 and 21. I could call it more than one time. Go ahead. You do when you're doing, not to set something equal to something, but you use an equal sign for primitive comparisons. Boolean, it's the Boolean operator. Yep. Yeah. Is it might be this? Yeah, I think it's semicolon. So it's actually this whole thing. Yeah, you get a semicolon followed by this exact sequence of characters. Yeah, and then you can put your comment after that. Yeah. No, just semicolon. It's not that early. I had my first pick up a parking spot at 6:15. And I couldn't get my coffee machine working. I know. And then I had to wash out my mug, but then the top, my coffee machine makes like the coffee, but then has like a, it's like a special kind of coffee machine. So it has like all the frothy stuff on top. But then I put my cream in, but the cream floats on top of it. So then your first like 11 sips are all cream. So you got to shake this thing up because I don't have a spoon. Yeah, what's that? I don't have a straw either. Because what we're really saying is at 6:15 in the morning, I should have texted Blade. Yeah. And had him come over and stir my coffee. Go ahead. Oh, just because it shows that you can put a value inside of, because I mean, I could say define nums2 to be a 6. Yeah, this is when you define something, it's variable name, value.
Okay, but if we still know, like, you can create a function without it being a lambda.
You cannot create a function unless it's a lambda is a function. Yeah, that, so when, again, so this is like a list, right? So that guy right there is a list. And if you don't have a little quote in front of it, what do we do to lists? We look at the very first element and you say, what is it that this dude does? I see the word lambda there, right off the bat that says this is a function. Lambda means it's a function. Isn't it interesting how almost anything that is like part of the Greek alphabet immediately seems intimidating? Why is that?
It's because people think that Greek alphabet is cool, where they name hard things after Greek alphabet.
Yeah, because even like because I don't know if it's making the news yet, but I was reading some article yesterday. They've discovered another variant of COVID, right? So this is the mu variant. Mu. Yeah, one of the Greek letters. Yeah. It looks like an M with the far left thing, like an extra long, kind of like a reverse J. The uppercase Greek letters look way less cool. Lowercase ones look a lot cooler. You should know the Greek alphabet. It's an important parlor trick to perform at bars. What's up? Oh, you got to know all of them. Yeah.
Take all the Greeks.
I'm listening to you. I'm just ignoring him. Yeah, go ahead.
So I could do some like order operations because they wanted to have like 3 variables at A and B that's subtract C. So
Okay.
plus sign.
All right. So you want to do take in 3 parameters, A, B, and C, and you want to what?
A and B subtract C. Yeah. How would that?
Right there. Oh, you guys think this is bad? It's going to get so much worse. Now, hold on. I am going to show you something that will make life, it'll feel a little bit better. I'm going to define something. Hold on. Let me do some spacing things here. Okay. So I'm going to kick it down. So this guy now takes in, it's a lambda. Here's the body of it. And then if it makes you feel better, you can do something like that. So here's the lambda. This is the first thing. It's a, I mean, you don't have to space it all like this, but you might say, okay, this is the first thing I'm applying. I'm applying it to 2 things. This is the first thing. This is the second thing. And if you want, you can kick this down and, you know, something like this. I usually don't go to that extent, but a lot of times you might bump it down a couple of lines so you don't have just a wall of parentheses. Yeah.
So the thing about doing that mental stretch is the first thing you write is the last thing that you do. So subtract is the last thing you do. So that's the first thing you put down.
Well, yeah, but that's not the rationale behind it. What are we doing right here? We are applying the minus function to 2 parameters, to 2 inputs. What are the 2 inputs? Well, this is the first input. Well, in order to get the answer of this input, I have to apply the plus function to A and B. So this guy doesn't become a value until we've done that, which is why this technically happens before this can finish. So it's a recursively defined data structure. But when you walk through it that way, I mean, it does make sense. You know, what am I subtracting? I'm subtracting this promise, something that's going to be a value, some kind of value. I can't do the subtraction until that dude's done, right? And I'm subtracting from it the value of this. This is even something that's not done yet. We have to resolve C to its value from the variable environment that's behind the scenes. So this really isn't any different than you might see in like Java or C++. You would still need to resolve those things. So if you were doing this in Java, you might say, you know, int r is equal to A plus B minus C, something like that. You're still doing this before you're doing this. And it's not just because of the, well, I guess if you had the parentheses, if you didn't put the parentheses in there, then it would do left to right in this case. But what you wanted to subtract is the addition of those two, well, C from the addition of those two things. So before you can do this, you still had to complete this. Does that make sense? Yeah, so it actually isn't different. It just looks intimidating because it's in a different format. Yeah, it's a programming language. I mean, you might sometimes need to do a little bit of twisting and turning. I would say if there's one thing that's probably going to frustrate you the most with Scheme initially, is that it is in traditional programming languages, you're used to just updating the values in a variable, just kind of willy-nilly whenever you want. Scheme, there is a way to do it, but it's actually not a common way to solve problems in Scheme. Typically, if you're going to have a variable whose value is going to change, that's going to result in a recursive call to the function with I minus 1 as the new parameter coming in. That's how you got a new version of the variable, by passing it into the function another time. And we'll see that through examples, but that's going to be that one omission where you won't solve problems where you're updating the value of variables while as part of your solution. Something like that. But the generic answer to your question is, yeah, it's a programming language. You can solve anything you can solve with other languages with it. Keeping in mind that with any programming language, we're always solving problems in terms of the tools we have available to us. And kind of by default, Scheme has a smaller toolbox, which is kind of why I think it makes it interesting in a class like this, because you don't have these powerful constructs that allow you to do like a lot of the heavy lifting for you. You have to get in there and kind of granularly do things, but it's not so bad that it's like programming in zeros and ones, right? You know, it's still a high level language. It just feels a little bit abstract, something like that. Go ahead.
Why don't they just do like adding like you would in other?
Well, how do you want, what do
Why
you,
would it be like plus 80 versus like?
so you want it to be like A plus B?
Yeah, it's easier to read.
Well, it might be easier for you to read, but think about if you had to write the interpreter for this. A little bit ago, I mentioned if you have a list, what it does is it looks at the car of the list and says, what is it that you want me to do? And if what you want it to do is A, the assumption is A is associated with some sort of function call, right? Now, a human being can look at this and say, oh, I'm doing A plus B. You know, our parser inside of our brain can look at that and say, oh, I know what you mean. But if you're thinking about this from a programming language perspective, what am I doing? I'm doing this to these things. Perform the car to the elements contained in the coder. That make sense? Go ahead.
Oh, if you ask for the car of plus AB, is that right? So who would it be? Would it turn out B plus, or would it turn out?
So you want me to take the car of this guy? That will give me a lambda.
It will say lambda, or it will turn out.
It probably should give me a lambda. Oh, give me a moment. I'll just put some numbers in there. It changed to the 3. Stop making me change my crap here. We're just going to get rid of all that. There we go. So I actually need to do the car of the car. No. Yeah, no, let's think about this. Because this is being applied to a list. The answer, okay, so what I said is correct. The car of this list is the lambda that is the built-in plus sign. So if I just say plus here, no, it is what you want. They're just making it look pretty. If I do choose language, I make it look different. I wonder if I have to run this again real quick. Yeah. I promise this is behind the scenes of Lambda. It's just not showing it in the thing. We'll get to a point where it'll show kind of like a cryptic thing with like placeholders and stuff. So you'll see that the stuff is stored in a structural way. But we should be able to pull it off because what you want me to do is take the car of this list, but it needs to be treated as a list first. Let's see. Here, let me see if I can fake it here. All right, so this is I want the footer of that list. I want the car of the cutter, the catter. So the cutter will be this guy, the car of it will be this guy. Let's see what we can get out of that. Let's see, it's quoting it, it's carrying this quote through. There's a way to get at the lambda of it as a built-in type. I think I switched it back, didn't I? Yeah, same thing. It's carrying this quote through. So I would need to do it like this, but then it's, it's going to say, well, there isn't a function named 2. Well, first it's going to complain about if I go like that, it's going to say, I don't know about a function named 2. But received a 2, it expected a function call. Never heard of this guy. Yeah, I could define, I mean, at least I believe so. Define 2 to be 6. Actually, because 2 is a reserved value, I don't think you can do that, but let's see if I can do it. Because the real question you're asking is, can you start a variable name with a number? Most languages you can't. Let's see if we can in here. We can in here. So Scheme allows you to have variable names that begin with a number. But I would not be able to redefine the int literal 2 to now be a 6. But oh, was there a question? I thought I saw a hand swing around. Okay. So in any case, the answer to your question logically is the car of that list would be a lambda. We have to stumble upon the syntax that allows you to extract that. We would be able to extract it from our own. I think if I said the car of lambda x, something like that. Oh, no, because this is, you see what it's doing is, and this is what happened before too. This goes back to his question with like order of operation. It's boiling this down first. So this is passing in a 2 as a parameter x to this function. So this whole thing here boils down to a 2. And I'm trying to take the car of a 2. If I instead created a list out of this x, now this works because I'm passing a 2 in for x here. What am I doing with the 2? I'm turning it into the list containing a 2, and then I'm taking the car of that list, which is a 2. with car. Because car is going to want to apply this. Even though you can pass lambdas in as parameters. And I can show you the passing of lambdas in as parameters. So I can say define, do something to be a lambda that takes in a func. And then let's see, let's call it takes in a func, and a val. And it calls that func on that val. All right, so the first element of this guy is a lambda. And then the parameter I'm going to pass that lambda is a lambda x along with a, I don't know, a 4. So the function I'm calling is that guy. This guy takes in 2 parameters. The first one's called func. The second one's called val. Func is this dude. Val is this dude. What's the body of this function do? It takes func and applies it to val. So this is going to boil down to just a 4. Oh, what I need to call it. Because the 2 parameters passed in here, parameter 1 is a function. Parameter 2 is the number 4. This was the function. This was the number 4. What am I doing in the body of this guy up here? I'm taking whatever func was and applying it to the single parameter that is val. So that is, I'm passing 4 in to this function, which takes in a 4 and does what with it? Just spits out the 4. If I want to do something more interesting, I could say like whatever the parameter is times 2, and now I'll get an 8. All right, but so the evidence there is that you can pass functions in as parameters to other functions. And if you want to see this maybe written in a little bit different way, I'll define do something like this. And the 2 parameters I'll pass it are this guy and this guy. So now do something is just a plain Jane function. It's a lambda that takes in 2 parameters and applies the first parameter to the second parameter. Now, when I call do something, I'll pass it the first parameter, which is a function, and then the second parameter, which is a 4. And I'll get my 8 out of that. But now, because I've written do something in such a way that it takes in 2 parameters, it assumes the first one will be a function. But now I can call do something, passing it a different function. So here's a second call to do something. I can have it take in a b and have it boil down to the list b, 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 something like that. And I'll pass it a 3 here. And then we get the list 3 through 3. So do something is a function that takes in a function and a value. In this case, my first call to do something, I'm passing it this function and this value. My second call to do something, I'm passing it this different function and this value. Go ahead.
How long do you think it's gonna take? Or how long are you expecting it to take before
Yes.
the language is-
yesterday. I did warn you that you're going to hate this for like 3 weeks, but it's going to be fun. And you're going to see, we'll probably get to one here today. The first several assignments are like little puzzle homework assignments that start off easy and then become cry yourself to sleep kind of stuff. But the first many assignments are built to have you practice with Scheme until you kind of get comfortable with it. So right now I'm kind of just showing you the kind of the high level stuff and trying to get you. I mean, if we were going to associate this back to something from like CSC470, it's that skill of making sure you look at code and say, what does this resolve to, before I just assume that what the output's going to be. Because as human beings, we're so, we might look at something and at a glance, we think it looks like one thing, but it actually is something else. If we took our time and said, this is a function right here. This function takes in 2 parameters. If you don't like me, I can call them A and B here. And then I can take A and apply it to whatever B was. Nothing changed logically in here. I just didn't name my first parameter func. I named it A. I didn't name my second parameter val. I named it B. But because of what I'm seeing in here without a quote, the way lists work is it treats whatever's the first element as a function and applies it to the rest of the elements as its parameters. So now I have a variable associated with an unnamed function, but I've given a name to it now with define. And this guy takes in 2 parameters. The first parameter is then applied to the second parameter as a parameter. So now when I call that function, I always pass it 2 inputs because it expected 2 inputs. That's what this Lambda expects. Give me 2 inputs and it's going to do this stuff. So in this case, this is my first input. This is my second input. It's going to apply this function to this parameter. A 4 will come in for the x. 4 times 2 is 8. This will give me an 8. The second time I call this function, I'm passing it this different function with this parameter. So a 3 will come in for the b. And what will the body of this do? It'll create a list of 3 b's, which is 3. List 3 through 3. Okay, so it's going to be that practice of slowing down and saying, what does this resolve to? Instead of at a glance, because you're not going to be as practiced at looking at this stuff with all these parentheses and stuff like that and seeing it at a glance. All right. But to answer your question, you should already be a master of this. It should already make plenty of sense, no confusion whatsoever. By the end, most students really like it, but there is that initial terrifying thing. Okay. We're going to be okay. So when we talk about creating programming languages in general, I think I mentioned this last class. In here, we're going to be writing an interpreter as opposed to a compiler, because we'll actually have something in here that can solve real problems with an interpreter, where if we were writing a compiler, which is really cool to write compilers, but it takes a lot more work to get a lot less out of it. Compilers are very, 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 very complex critters. And evidence is in, if you look at, the compiled languages that exist today versus the interpreted languages, our compiled languages rarely change. We have our kind of our core group of, C, C++, Java, C#, Swift, Objective-C, and they kind of stick around. Where our interpreted languages, a new one comes out every 15 minutes, right? Somebody's writing an interpreter for that, that's like, oh, it's like Python, but, Google has their Go language now. It's like a new language comes out often because interpreters are very easy to write, relatively speaking, to a compiler, because they're written using a high-level compiled language most of the time. Okay. So we're going to be writing an interpreter in here. So we'll be creating a language that's more like a Python than like a Java. Although I do typically make the languages in here, and we'll see. It all depends on the mood when we first do it. I usually make it list-based in here rather than making it look more like Python. So we almost end up writing our own version of scheme inside of scheme, but with different syntax. Which, trust me, is actually the easier way of doing it. Because you're getting to use some of scheme's built-in stuff without trying to like force it into making your code look like string tokens, like you would see in Java, non-list based stuff. So even though it sounds worse, writing scheme in scheme is actually a pretty easy thing to do. Actually, it would be a super easy thing to do because you can do the whole thing in a single lambda. Whatever the input is, apply it to the other parameters. That's scheme. If you're using scheme to write scheme, whatever you pass in, you can just pass it to the scheme interpreter. You already have the interpreter.
That's not what
No, that would be too easy. We're writing a scheme-esque language. So something kind of in the middle, where you'll still get to invent your own syntax for like what an if statement is. And, you know, a lot of times we'll call it like a question. You know, an if statement is called a question instead of if, it'll be question. And because the first thing is question, this is what we do to questions. And we'll have to invent what does it mean for something to be a Boolean expression and those kinds of things. Okay, and in previous classes, we've talked about interpreters versus compilers. Interpreters are relatively slow. Compilers are relatively fast. Computers today are really fast. So it doesn't really matter at the end of the day. All right, but our focus in here are the constructs that build up a programming language so that when you go back and you write traditional code, you have a greater skill of knowing what is actually happening under the hood, because sometimes that will help explain something that is behaving, let's say, kind of funny, and you're wondering, well, why does the language work this way? What was the design decision they went through to decide that, oh, it's going to do this under a certain circumstance versus something else? And it will help you solve, you know, it's not going to be like the super common thing, but in industry, let's say that, you know, 95% of all the problems you solve are going to fit into that category of straightforward, mundane, might be a little bit on the complex problem solving side, but nothing earth shattering. But then you get to that 5%, just some kind of a weird problem. You're having to think like, how can I leverage this programming language to kind of solve this weird thing? And the more you know about what's happening under the hood, the more weapons you have in order to accomplish that kind of thing. Time. We kind of just said that. Okay, this is just review stuff. 3 kinds of programming languages: machine language, low level, high level. Scheme is a high level language. Kind of your question about can you solve things in scheme like you could solve in any other language? The answer is yes. So it's a high level modern programming language. It probably behaves to a programmer who's just being introduced to it. And for us, you ask the question of, you know, how long until you should get the hang of this? The reason this feels uncomfortable to you is because this is probably the first time you're being exposed to a functional language as opposed to a procedural or object-oriented language. And it's not that the language is drastically different, but you're having to think about things in terms of function calls and what they boil down to. It just follows kind of a different cadence that you're not used to. It's a different classification of language, even though it's still a high level language. And scheme is also a much smaller language, even though it's bigger than Lisp. So scheme is what's called a superset of Lisp. So Lisp is an older language that kind of came out for early artificial intelligence problems. And then Scheme took Lisp and said, hey, let's add some extra crap. And then we have Scheme. Yeah.
No, you just said this, but I don't understand. Scheme is not an object.
Let's say no. You can technically pull off objects in it. We will be using Scheme to make our language an object-oriented language. Near the end, we'll be creating our own objects, which actually isn't overly difficult. You know, we've already had some of the punchline with that today, where what's a class? Class is kind of like a function, and we could store it inside of a variable. You know, so we can build a constructor for a generic class and put it into our variable environment. So now we have a tool that can generate a class. These things end up sounding complex, but at the end of the day, what's a class? A class has a name, it has a set of fields, it has a constructor, one or more constructors, and it has 0 or more methods. You know, think of it like a big toaster. You just drop those things in and now you have a class. An instance of a class. So it's a lambda that takes all those things as parameters. It's just prefabricated so that when you go to build a class, you can just say, okay, well, here's the information it requires for it to work, plop, 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 and now it's good to go. And figure out how do I store that in my variable environment. All right, humans like power tools, yada, yada, yada. Remember compilers, they convert a high level language into a low level language, ultimately to zeros and ones at the machine level, whereas an interpreted language, what we're going to do here, basically just translates from a high level language into the logic that you want it to accomplish. That's why it's relatively slow. All right, we talked about this last time. You know, we're going to be trying to target memory, asking questions and repetition. So we're going to be looking, once we get past kind of the practice with Scheme stuff, we'll be looking at how do you write a variable environment. We'll have different versions of variable environments, ones that start off with, hey, let's just get something sort of kind of working, to what if we think about variable scope, where variables need to resolve to their most local definition. How does that throw a wrench into the thing? Same thing with conditionals, repetition. We'll do a lot of recursion in here. All right, so now this is kind of stuff we've already worked with. Let me just show you these two other things here, list and append. You actually saw me use list today. So let me just define LST1 to be the list 1, 2, 3. I'll define LST2 to be the list 4, 5, 6. I'll go ahead and run that. All right, so now if I type in LST1, we see it's just showing me the value associated with the variable LST1. Same thing, LST2, it's showing me the value associated with the variable LST2. Now, if I want to create a list out of LST1 and LST2, it's going to, so this, the list function takes as parameters one or more elements and makes a list out of them. So this will create a to list, that is a list with 2 elements in it, where this guy is the first element, this guy is the second element. So here's a list. There's element 0, there's element 1. Didn't combine them or anything. It just made a list with these 2 things in it. These 2 things happen to be lists, but nothing kept me from saying make a list out of 2, 3, 4. Go ahead. Yes, you can, but we haven't done it yet. And we're not going to do it for a while. We probably write our own function to do it at first, where you just do cars and cooters until you got to the place you wanted. But there is a function built in that allows you to do it. All right, so this list function here allows you to wrap stuff into a list. So I can create a list out of 2, 3, 4 like that. I can accomplish the same thing with another function called the cons function, which is a constructor. It constructs a list. So I can cons a cons onto the cons of 3, onto the cons of 4, onto the empty list. So the cons function requires some value, some element, doesn't matter what kind of element it is, just any kind of element, but the second parameter must be a list. So this is going to cons a 4 onto the empty list, which means that this guy right here will turn into the list containing a 4. This guy right here will turn into the list containing 3, 4, because I'm consing a 3 onto the list containing a 4. This guy right here will turn into the list 2, 3, 4, because I'm consing a 2 onto the list containing 3 and 4. So these two lines ultimately will give me the same output. List 2, 3, 4, list 2, 3, 4. So I'm constructing a list right here, which is going to be an important thing for us. We're going to be using this a lot. Because as we start writing functions, we will be consing a current value onto probably a recursive call for do the next thing. Okay, we'll see examples of that. All right, then append. So if I create a list out of 2, 3, 4, or here's another example, if I cons LST1 onto LST2. Here's LST1, here's LST2. If I'm consing this on there, what this will do is it will take this list as my second list, and it will cons this thing as the first element of the next list. So this will produce for me the list containing the list 1, 2, 3, followed by a 4, followed by a 5, followed by a 6. So 4 separate elements. First element being a list, next 3 elements being int literals. So when I cons LST1 onto LST2, I'm left with a new list containing what used to be an LST1 as the first element, and then all of LST2 as the rest. As opposed to append LST1, LST2. Append glues 2 lists together. So this will give me a single list containing 1, 2, 3, 4, 5, 6. When I use append with 2 lists. So append requires both parameters to be lists. And it merges those lists together into a single list. Okay, so effectively what we're doing here is we're running over to Home Depot, we're buying these tools. So we have a relatively small set of tools here. You know, we have car, we have coder, we have cons, we have list, we have append, we have if, and we have cons, even though we haven't practiced with those question ones very much yet. You know, but a relatively small number of wrenches sitting in front of us, and we apply those guys to different kinds of things. All right. We've started already. I'm going to bypass this for right now. We'll come back to it. So one of the things that we're going to be doing in here as we start defining or creating languages is we'll be creating functions that match certain languages. So this guy talks about what is a list of integers, right? So we've invented this language that says this is the language of lists of integers, where a list of integers is either the empty list or it's a list containing an int followed by another list of integers. This is recursively defined data. List of int is defined in terms of itself. So what are some examples of lists of integers? It's the empty list, or it's the list containing a 1, or it's the list containing a 1, 2, or the list containing a 1, 2, 3, so on and so forth. So this is a formal way of describing, these guys are called grammars, a formal way of describing a language. So after we get kind of past some of these practice things, we're going to start building up the grammar of our programming language. That's going to include like if statements, which we might call like a question, something like that. Yeah, so this is like an example of like the Lambda Calculus expression that we'll start off with. So a very simple programming language where we can either have a single identifier, which is kind of like a variable name, or we can have a function that's a lambda followed by a single parameter followed by its body, which is another Lambda Calculus expression. Or we can have a list containing a Lambda Calculus expression, another Lambda Calculus expression, where we would apply this function. So this guy here is very likely one of these guys to whatever this guy is, which might be an identifier or something like that. So this is a grammar, this whole thing we're looking at here. And each line here is called a production. These are productions within the grammar. All right, and we'll be using these a lot. So we'll see these through practice. All right, so this answers your question. You said, how do I get a certain element from the list? So you can do this thing called list ref, where I want, you have a list A, B, C, and you can pass the index you want. So it's a 0-based index, and it'll get you bucket 1. So in this case, I want bucket 1 from this list, which is a B. All right, now let's say we wanted to write our own procedure, though, called nth element. I mentioned that, why not just write it ourselves? Okay, now if we want to follow kind of the Java naming convention, maybe we write something called like index of, right? Because we're actually not index of, we would write char at. Char at would give us the thing we might be used to from Java. So we'll define char at to be a lambda that takes in a list and an index, right? And what we ultimately want to do is we want this guy to return the element in LST at bucket index. That make sense? All right. So anybody have some suggestions on how we might pull this off? It should still be probably pretty difficult for you to think about right now. But where effective, this is going to be our first example of recursively a recursive function. But I have a list like the list 1, 2, 3. And let's say I want bucket 1. So these are the 2 parameters passed in. How do I ultimately return the 2 from this guy without using that list index I just showed you? Okay, so he says I want to cutter this number of times until I get to, well, until this, once I cutter this number of times, then I want to take the car of what's left over. Okay, makes sense. That's the high level solution to it. Problem is we don't have loops. So how do I do something this number of times? Well, we also talked about defining variables and changing variables along the way is also a difficult thing. But I kind of mentioned that you could pass in those changes as calls to the function. So I might do something like if equals index 0, boil down carb list, else call char at on cutter of list and minus index 1. There's my 2. There's my 1. There's my 3. All right, so now let's look at what the heck just happened. All right, so function's name is char@. It's taking in 2 parameters, a list and the bucket in that list that I want to boil down to. I'm asking a question. If this bucket is currently equal to 0, if I've counted down to a 0, then what am I going to boil down to? The car of that. That's exactly what you said, right? Take the cdr some number of times until you finally hit the number of times you want to take it, and then give the car. So if index is counted down to a 0, then boil down to the car of that list. Otherwise, if it hasn't counted down to 0 yet, what am I going to do? I'm going to call my function recursively. So I'm going to call char@, again, passing it the cdr of that list, just like you said, right? Along with index -1. So I'm changing that variable as part of my call to the recursive function. So I went from 2 to 1 to 0. Each time through, in this kind of example, I went from 2. Is 2 equal to 0? It's not. So call char@, again, passing it the list 2, 3, and a 1. Is 1 equal to 0? It's not. So call char@, again, passing it the list 3, and a 0. Is 0 equal to 0? It is. Return the car of the list, which is the car of the list containing 3, which is a 3. So I use this guy to do my counting. This is effectively a loop that I just wrote recursively. Does that make sense? So now that we've walked through it, it should now make sense to you when you see it. And you should be able to, if you slow yourself down and do it one step at a time. What's our first call here? Char@ 1, 2, 3, and 2. We ask, is 2 equal to 0? No. So call char@ on 2, 3, and 1. Is 1 equal to 0? No. So call char@ on the list 3 and 0. Is 0 equal to 0? Yes. So boil down to the car of 3, which is 3. And that's our answer. This is the explanation of what is happening on this example call of this function. Good.
You know, I would do a loop. Every time you have a, like, every time you see a loop, it's always
Mhm.
is there like a structured way
This is the structured way.
okay. I just wasn't sure if this was the way.
Yeah, this is the way. So says the Mandalorian. You see the movie? Have you seen the show? Oh. Well, then you don't know what this is the way means. Feel included. All right. So effectively, to answer your original question, is there a way to get a certain element of a list? Sure, but why use it when you can just write your own? It was just that. And now you wrote something that sounds like what you're used to with Java. Char@. Give me the character that lives in a certain bucket. Instead of a string, it's a bucket of a list. Okay, so this one could be kind of a fun one to write. What time were you done? 20? Right, okay, then let's pause there. So I'll give you some practice to do. So first homework assignment, it's on the slides. I have the slides already linked up there. Here's 3 functions to write, 3 functions to practice. First one's called duple, which returns a list containing this many copies, n copies of whatever the second element is. So if I said duple of 2, 3, it's going to give me a list containing 2 3s. Duple of 4 ha-has, it's going to be a list containing 4 of the element ha-ha. So this is practice noticing that an element is just that. It can be anything that is a scheme value. It can be a number. It could be a char. It could be a list. It could be a list of lists. All right. So duple will create a list containing this many of these guys, whatever that guy is. So that's our first function we're going to write. Second one, invert. So this is where a list is a 2 list. So the guarantee here is that every parameter to this, so we have a list of 2 lists where each of these guys is exactly 2 elements. So you know you can get the first element with a car and the second element with a car of the cutter. Guaranteed, each one is a 2 list. All right. So returns a list with each 2 list reversed. So if I invert A1, A2, 1B, 2B, I'm left with the list containing 1A, 2A, B1, B2. Each of these 2 lists is inverted. All right. And you can do that by either creating a list of those guys or consing things onto the empty list. So that'll get practice with those 2 things. Last one is called down, wraps parentheses around each top level element. So down of 1, 2, and 3 should return the list containing the list version of this element, the list version of this element, the list version of this element. Make sense? All right, so for Tuesday, write these 3 functions. They're up on the slide. It's slide 36 right now, but it's labeled as homework 1. Questions, comments, concerns, bribes. Make sure you also send me the self-evaluation. It might be pretty handy in this case because you might stare at this for, I don't know, 17 to 35 hours. And then we come to class and we're going to solve it in like a minute. It's going to be so fun. Those are trust me. It'll start clicking.
So what's happening exactly in that last one?
Yeah, just if down the list 1, 2, 3 should turn into the list containing this guy as a list, this guy as a list, this guy as a list. You're wrapping each element in a list. Yeah. And the great thing is you can actually write this one as a single line. You won't, but I'll show you in class next time. Yeah, it's nobody will. Most people won't, but you could. Yeah.
Okay. I really think I'm overthinking the 543 assignment.
Okay.
Literally, is it just like a double array?
Which one are you on?
It's 2. So it's the 2D array, and the next one is the linked list. And
Okay.
the sparse matrix.
Yep.
It's literally just a 2D array. Like, that's it.
For the 2D array version of the sparse
Right.
matrix, yes, but it needs to work for different things coming in. So I mean,
Gotcha. So
it's a way of representing a sparse matrix in a way that you can then take that and you could explode it back out to the full.
Gotcha. So someone would like give you a sparse matrix, it would turn it into this and
Yep.
vice versa.
Yep.
Thank you. That's where I was looking at.
Just a quick question.
Sure.
So, the appends, like if you have 2 lists, so like 1, 2, 3, and 4, 5, 6, and you append them, it just turns to 1 list. So 1, 2, 3,
Yep.
4, 5, 6.
Concatenates them together.
Yeah, and for the cons, if you did 1, 2, 3, and 4, 5, 6, would be a list of 1, 2, 3, and then 4, 5, 6 is just
Separate things. Yep.
Do you know how you could like combine 2 lists to make like 1, 2, 3? If you have the first list is 1, 2, 3, the second list is 4, 5, 6. Have it be the output is 1, 2, 3, and then 4, 5, 6 in a bigger list. or what I just?
So you want to have a list containing two 3
Two
lists.
Yeah.
Yeah, 2 separate lists. So you would cons the 1, 2, 3 onto the list version of the second one. So you would wrap the second one in a list, effectively calling down on it, which we're writing here. So if you had the list 3, 4, 5, and you made it a list of that, now you have a list containing a single element, which is the list 1, 2, or 3, 4, 5. So a list of a list.
Okay.
And if you cons this list onto a list of a list, you're left with a list of 2 lists.
Okay. So would you like to start with?
I can show it to you here.
Okay.
So cons 1, 2, 3 onto the list of 4, 5, 6.
And doesn't that look like dash or whatever, like base? Do we need to say list there?
Oh, if you put
I
that-
purposely am saying list to answer your question.
Okay. Okay.
That's what you want.
Perfect.
Because what I'm doing here is I'm wrapping this list inside of another list. So this
Okay.
will create a list that contains one element. That one element is that dude.
Could you? Is it the same syntax, basically saying like 2 little dashes?
No,
No, you can't.
no,
do that?
yeah,
Okay.
can't do that.
But does it kind of mean the same?
No, because this guy doesn't say a list. This guy is a quote. It says, don't treat this as a function.
Okay.
That's what that single thing means. Don't treat this guy as a function.
Okay. Cool. That makes sense.
It just so happens that that will always be for a list.
Okay. Gotcha. Okay. Cool. Thank you very much. That helps.
Yep.
Senior project, I have had nice